Hi. So we're continuing our work on section 2.2 and limits, and we're going to talk about the precise definition of a limit. Now, in my class, I don't ask homework on this and won't be on quizzes or exams, but it's there for people who are interested. It's an important part of the subject. It's also there for people who are math majors continuing going on and want to hear the full story. And finally, it's also there just really for anybody who thinks, well, how exactly do you make the definition precise? Okay, so let's go to it. Let's see, bring that back up again. There we go. Okay, so again, the material is supplemental. In my class, it won't appear on quizzes or exams. So here's the formal definition. Let f be defined for x is near to the anchor number a. Then the limit as f of x approaches a is equal to L. When for every tolerance in the output, it's traditional to call the output tolerance epsilon, there exists a tolerance in the input, which is traditional to call the Greek letter delta. Sorry, spelled delta wrong. D-E-L-T-A. D-E-L-T-A, and that's epsilon. Epsilon, E-P-S-I-L-O-N. For every tolerance in the output epsilon, there's a tolerance in the input delta, such that if x minus a absolute value is less than delta, then f of x minus L absolute value is less than epsilon. If x is within delta of a, then f of x is within epsilon of L. Very important idea, very difficult to make out the first time you see it. Everybody struggles with this. It absolutely is a head scratcher. We're going to work through some examples, but full consequences of the definition really are kind of beyond us in the class, beyond the scope of the class. But I'm going to talk about it a little bit because it deserves it. It's important and it deserves it. So here is the output tolerance. This is L plus and minus epsilon. And down on the bottom is the input tolerance. This is A plus and minus delta. So given epsilon, can we find a delta sufficiently small that any x in the red interval maps under f? Any x in the red interval, like this one right here, maps under f, there's f of x, maps under f to be within the output tolerance. Okay. So the definition starts with a real function in anchor point A and then sets up a game. If a challenger gives us an output tolerance epsilon, can we respond with an input tolerance that's suitable? So if we show how for every epsilon there's a delta, then we win the game and we conclude that the limit as x approaches a of f of x is equal to L. Since it's a game, I've set it up as a computer game. It illustrates that the function, the anchor point, and the limit candidate are all parameters. They vary from problem to problem, but inside of a problem, they're fixed. Inside of a problem, we're challenged with an epsilon and you have to produce a delta. So there's this idea of parameter. Parameter is something that varies from problem to problem, but inside of any problem, it's fixed. Inside of the problem, though, the epsilons vary. Now, I made this game in the computer language Sage, the mathematics computer language Sage, the language that I like to work. It's based on Python, so for folks who are familiar with Python, probably this looks pretty familiar. I'm not going to go through the code. You can read the code on your own if you're interested. That's perfectly fine. But instead, I'm going to do an example of working through the game. So I'm going to start with one that's frozen into the slides. So I'm going to bring in the epsilon-delta code that you just saw. Then I'll define a function. It happens to be the squaring function. And I'll start a game that depends on that function I just defined. On the input, a equals 4, a equals 4, a equals 4. And on the output, L equals 16. 16, there we go. I didn't do a very good job on the 16. Still didn't do a good job, but I'm going to skip it. And then you enter an epsilon, and you're given some deltas to try, and the system tells you whether the deltas are good enough. And either the delta works or it doesn't work. Okay, this particular, each round of the game ends when you find a delta that works. All right, let me bring up an example of the game. You see that same thing. It says attach epsilon delta Sage. That's how you bring the code in. And I'm going to define a function in the slide here. I define the function f of x equals x squared, so I'll define it again. So define f of x, and I'm going to return x squared. Whoops. Okay, and now I'm going to play the game. In the slide that I just saw, I decided to take a equals 4 and L equals 16. Now I'm going to take a equals 5 and L equals 25. So I'm going to play the game, EPSDEL, F 5, 25. Okay, and the game says enter an epsilon, so I'm going to enter an epsilon. I'm going to try 0.01, just for an example of a small number. And now I'm going to be challenged to come up with a delta that suffices to beat the epsilon of 0.01. So I've got to try various small numbers until I come up with one small enough to win. And I'll remind you what the picture is in just a second after I find a delta that works. So let me try 0.1 and see if that works. No, that's not enough. 0.01, that got good. Not small enough. 0.001, is that good? Not small enough. Let's go 0.00001. Just sure that had to be small enough. I mean, come on, that was pretty small. Okay, so just to remind a person now of what's happening here, if I can get back to my, there we go, back to my screen, and I want to go to the previous page. There we go. Okay, so what's happening here is that I'm being given an epsilon of 0.01. Epsilon is 0.01. 0.01 is that distance there, and I've got to come up with a delta. So a small enough tolerance around a equals 5 to make that all x's inside that interval are within 0.01 of 25. All x's inside that interval are within 0.01 of 25. And what I found is that if I take 5 plus and minus 0.0000, I don't remember how many O's, a lot of O's, and a 1, then sure enough, every such x is within 0.01 of 25. Okay. Now on the one that's frozen in the slide, I took epsilon equals 0.01, and it turned out that a delta that was small enough was 0.001. A person should ask, what if there is, what if you pick a limit that's wrong? So what if, for example, you took tried to play the game with a equals 4, but the limit is not 16, not 4 squared, but instead 10. So that's what I've got here. I've got the f of x equals x squared. And what would happen if you try to say something like the limit as x approaches 4 of f is 10? Well, that's not right. So how does the system tell you that that's not right? And the answer is you try an epsilon 0.01, and you keep looking for deltas, and it keeps saying you failed. You can never find a delta that works. You can never find a tolerance of 4 small enough, a tolerance around 4 small enough to ensure that f of x is always within 0.01 of 10. Then that's not going to happen. Okay, so the idea is that someone challenges you with an epsilon, and you've got to produce a delta small enough. Can you make delta be whatever the heck 1? And the answer is if the limit is wrong, you can't. In general, just kind of as a general picture, given an epsilon, how do you choose delta? So I have kind of a vague hand-wavy thing because that's all we're doing here. So we're challenged with an output tolerance, we're challenged with an epsilon, and we've got to produce the appropriate delta. There's A comma L, and we're going to be challenged with an epsilon. I drew epsilon on the slide. We've got to produce an appropriate delta. So what might a person try? So here's what a person might try. You might try, you find the tangent line to the graph. We've done the slope of that line a number of times. So we find the tangent line for the graph, and you use that as an approximation for the function. Okay? I'm going to draw here the plus and minus epsilon as horizontal lines because I'm going to want to do something with them. And what I'm going to do specifically is with those horizontal lines, I found the intersection with the tangent line right there, and I dropped a perpendicular. And it comes out down here. Okay, so again, here is the here is L minus epsilon where it intersects the tangent line, and I dropped a perpendicular. And there I am right there. Okay, I took the one closest to A because there's another place if you drop a perpendicular here, but I'm going to ignore that. I took the one that's closest to A. Closest to A. The triangle up here, this triangle right here, this triangle's right there, that triangle slope is epsilon over delta x. So this distance right here is epsilon over the absolute value of the slope. Take delta to be half of that. So this distance from where I dropped the perpendicular to here, this distance right here is epsilon over the absolute value of the slope. Take delta to be half of that, and what you get then is this interval a minus delta, a plus delta suffices. And you can see in the drawing, in the rough diagram, that any x you picked in here is going to give you an f of x that is indeed in the desired output tolerance. I can't make the arrows. I'm going to give it a f of x that's in the desired output tolerance. Okay. So very hand wavy, all very, do this, do that, without any real explanation. But that gives you some idea that given an epsilon, there is somehow a way to choose a delta that's somehow likely to give you the right answer, systematically give you the right answer. Finally, to be completely precise, and again, all this is optional, not going to be on quizzes or exams. So if you're feeling like I got lots of other things to do and this is a little bit too much, fair, all perfectly fair. But for those folks who are interested, particularly math majors, I'm going to do a full example here for the simplest case, the case of a function whose graph is a line. So f of x is minus 3x plus 2, and I want to show that if you take the limit as x goes to 4 of f of x, you get minus 10. And of course, minus 3 times 4 would give minus 12, plus 2 gives minus 10, so that tells you it's the right answer. So I'm going to follow the method on the prior slide. Of course, the function's rate of change, the slope is minus 3. So, oops, there we go. The function's rate of change, the slope is minus 3. So given epsilon, I'm going to take delta to be half of epsilon over the absolute value of minus 3. So epsilon over 6. Okay. And then I've got to show that if x minus a, in this case that's x minus 4, absolute value is less than epsilon over 6, then f of x minus L, in this case that's f of x minus negative 10, is less than epsilon. So I'm going to suppose that x is within, that x satisfies this condition. So there's x satisfying the condition. It's between negative epsilon over 6 and positive epsilon over 6. And now just going to do some algebra. I'm going to multiply both sides by minus 3. Notice that the multiplying by a minus changes the inequality's directions. So multiply both sides by minus 3. X minus 4 multiplied by minus 3 makes minus 3x plus 12. Negative epsilon over 6 multiplied by minus 3 gives you epsilon over 2. Epsilon over 6 multiplied by minus 3 gives you negative epsilon over 2. And I'm, of course, not really interested in the function minus 3x plus 12. I'm interested in the function minus 3x plus 2 because, have you forgotten? Here it is. That's the function on the top of the slide. I rewrite this to bring out the minus 3x plus 2, and I have minus 3x plus 2 plus 10. Well, that's minus 3x plus 2 minus a negative 10. And that brings me down to here. F of x minus L is between epsilon over 2 and minus epsilon over 2, which automatically puts it between epsilon and minus epsilon. So if x satisfies this condition here, then automatically f of x satisfies this condition here. So what we've shown is we've given a strategy and proved that it works, that if somebody gives you an epsilon, if they give you 0.03, then you know how to choose delta. You would take 0.03 and divide it by 6. Okay. Now, please, I absolutely concede that the formal definition of a limit is something that a person has to study for quite some time before they really kind of have it down. This is just a quick go through, which is why we're not having it on a quiz or exam. But nonetheless, just to have done it to say to yourself, well, I see how you could make the definition precise if you wanted to. Okay, very good. So we'll start in on the rules for applying limits next time.